Subscribe to the channel so you don't miss out on any of these videos. Imagine a phenomenon so strange, so counterintuitive, that it seems to defy the very laws of physics we rely on to explain the universe. This isn't science fiction. It's happening right now, in every single star you see in the night sky. It's called quantum tunneling, and it's one of the most fascinating, mind-bending mechanisms in nature. Without it, stars wouldn't shine, life wouldn't exist, and the universe as we know it would be a completely different place. But here's the kicker: quantum tunneling doesn't obey the rules of classical physics. It's a doorway to a world where particles slip through barriers they have no business crossing, literally changing the course of cosmic evolution in the process. Now, think about this for a second. Stars, those blazing beacons of light billions of miles away, don't generate energy because of brute force. They do it because of an invisible trick, something that can only be explained through the bizarre and unpredictable rules of quantum mechanics. Why does this matter? Because it means that at the very heart of the universe, everything we thought we understood about how energy works gets flipped on its head. And today, we're going to dive into this mystery, peeling back layer after layer to uncover how quantum tunneling fuels the stars and sustains the cosmos. So what exactly is quantum tunneling, and why is it the unsung hero of stellar fusion? Let's start with the basics. Deep inside the core of a star, where temperatures soar into millions of degrees and pressures are unimaginably intense, atomic nuclei are packed together so tightly that they constantly collide. Normally, these collisions would just result in particles bouncing off each other because of something called the Coulomb barrier. This is an invisible force field created by the positively charged protons within the nucleus, which naturally repel each other, kind of like trying to push two magnets with the same poles together. Classical physics tells us that for two nuclei to overcome this repulsion and fuse together, they need an enormous amount of energy. Here's the catch: even in the extreme environment of a star's core, the particles don't have enough energy to break through the Coulomb barrier. At least, not according to classical physics. So how does fusion happen at all? Enter quantum tunneling. Quantum tunneling allows particles to bypass the normal rules of physics. Instead of having to climb over the wall of the Coulomb barrier, they essentially sneak through it, as if the wall wasn't even there. It's like watching someone walk through a solid brick wall instead of opening the door, an act that seems impossible but, on a quantum scale, is just another day at the office. This bizarre process happens because of a principle called wave-particle duality, which states that particles like protons and electrons don't just behave like tiny solid objects, they also behave like waves. And waves, as you might know, can spread out and overlap, even appearing on the other side of obstacles. The odds of a single particle tunneling through a barrier are small, but in the dense and chaotic environment of a star, where countless collisions occur every second, quantum tunneling becomes inevitable. When a proton successfully tunnels through the Coulomb barrier and fuses with another nucleus, it releases a massive amount of energy in the form of light and heat. This process is the foundation of stellar fusion, the reaction that powers every star in the universe, including our own sun. But there's more to this story than just the mechanics of tunneling. Quantum tunneling doesn't just allow stars to shine, it also sets the stage for the creation of every element in the universe. Stars begin their lives by fusing hydrogen into helium, but as they evolve, they start producing heavier elements like carbon, oxygen, and iron. These elements are forged in the extreme conditions of stellar interiors and later scattered across the universe when stars die in explosive supernovae. Without quantum tunneling, none of this would be possible. There would be no stars, no planets, and no life as we know it. Now, here's the wild part. Scientists have known about quantum tunneling for decades, but we're still unraveling its mysteries. For example, how does tunneling work on scales beyond individual particles? Could it help explain other cosmic phenomena, like the behavior of black holes or the nature of dark matter? And is it possible to harness quantum tunneling for energy production here on Earth? These questions push the boundaries of what we know, forcing us to rethink not just the physics of the universe but the nature of reality itself. What makes quantum tunneling even more fascinating is that it challenges our intuition. In our everyday lives, we're used to thinking of objects as solid and immovable. A car can't suddenly appear on the other side of a wall, and a ball can't roll uphill without an external force. But in the quantum world, particles routinely do things that seem impossible. They teleport, they exist in multiple places at once, and they defy the barriers that should hold them back. This isn't just a curiosity, it's a fundamental aspect of how the universe works. Take a moment to consider what this means. Every photon of light that has ever reached your eyes, every star that has ever lit up the night sky, owes its existence to quantum tunneling. Without this strange quantum behavior, the universe would be a cold, dark expanse, devoid of the energy and complexity we take for granted. It's a humbling reminder that the most important processes in nature often happen on scales we can barely comprehend. And yet, quantum tunneling isn't limited to stars. It's a universal phenomenon, appearing in everything from the behavior of semiconductors in your smartphone to the chemical reactions that sustain life. In fact, tunneling plays a crucial role in enzyme activity, allowing biological processes to happen faster than they otherwise could. It's another example of how the quantum world intersects with our everyday reality, shaping the universe in ways we're only beginning to understand. But let's get back to the stars. One of the biggest challenges in understanding quantum tunneling is that it operates in a realm where our traditional physics breaks down. The equations that describe tunneling rely on quantum mechanics, a branch of physics that deals with probabilities rather than certainties. This makes it difficult to predict exactly how tunneling will behave in different situations, especially in the extreme and chaotic environment of a star's core. Despite this, scientists have developed sophisticated models to simulate tunneling and its effects, providing insights into the life cycles of stars and the evolution of galaxies. In recent years, advances in technology have allowed researchers to study tunneling more closely than ever before. Experiments with particle accelerators and quantum computers are shedding light on the underlying mechanics of this process, revealing new connections between the quantum and classical worlds. These discoveries not only deepen our understanding of the universe but also pave the way for practical applications, from energy production to quantum computing. The potential implications of understanding quantum tunneling stretch far beyond what we currently know. For stars, quantum tunneling is the lifeblood of their existence, driving the nuclear fusion reactions that sustain their luminosity for billions of years. But the concept also inspires new questions about the very fabric of the universe. How did this mechanism become such a critical part of cosmic evolution? Could it operate differently under unique conditions, such as in the presence of dark energy, or near black holes? These are the kinds of questions that keep astrophysicists awake at night. One of the most intriguing aspects of quantum tunneling in stars is how it plays into the fine-tuning problem of the universe. The conditions required for tunneling to occur, such as the temperature and pressure inside a star, are extraordinarily specific. If the forces governing particle interactions, like the strong nuclear force or electromagnetic force, were even slightly different, quantum tunneling might not occur at all. Without tunneling, stars wouldn't ignite, and the universe would be a vastly different, and likely lifeless, place. This delicate balance raises profound questions about the nature of reality, and why the universe's fundamental constants seem perfectly suited for life. In stars like our Sun, quantum tunneling primarily drives the fusion of hydrogen nuclei, protons, into helium. This is the first step in a series of reactions collectively known as the proton-proton chain, which produces the energy that powers the Sun. The proton-proton chain is incredibly efficient, but only because tunneling allows protons to bypass the Coulomb barrier. Without tunneling, protons would almost never get close enough to fuse, and the Sun would be incapable of producing the energy needed to sustain its light and heat. It's worth noting that the odds of a single proton successfully tunneling through the Coulomb barrier are minuscule, on the order of 1 in a billion. Yet, because the Sun contains an astronomical number of particles and conditions for fusion are constant, these improbable events add up to produce the energy we see. The tunneling process also plays a crucial role in more massive stars, where heavier elements are synthesized. These stars rely on a different fusion process called the CNO, carbon-nitrogen-oxygen, cycle, which operates at higher temperatures and pressures. While the CNO cycle involves a more complex sequence of reactions, quantum tunneling is still the key mechanism that allows nuclei to overcome their mutual repulsion and fuse. Without it, even these giant stars would fail to ignite, and the universe would be deprived of the elements needed to form planets, oceans, and eventually life. Quantum tunneling's influence doesn't stop at individual stars. It also affects the broader dynamics of galaxies and the cosmos. The energy produced by fusion in stars generates the light and heat that we observe across the universe, but it also drives stellar winds, supernovae, and other processes that shape the interstellar medium. These processes, in turn, play a critical role in star formation, the distribution of elements, and the overall structure of galaxies. In this way, quantum tunneling serves as a cornerstone of cosmic evolution, linking the smallest scales of particle interactions to the largest structures in the universe. But here's where things get even more fascinating. Scientists are beginning to explore how quantum tunneling might operate in extreme environments, such as in neutron stars or near the event horizons of black holes. These objects represent the limits of physics, where the known laws of nature start to break down. Could tunneling occur differently in such extreme conditions? For example, in a neutron star, where matter is compressed to densities millions of times greater than in a star's core, the behavior of particles might change in unexpected ways. Understanding tunneling in these contexts could provide new insights into the fundamental nature of matter and energy. Another area of interest is the potential connection between quantum tunneling and dark matter. Dark matter is one of the biggest mysteries in modern physics. We know it exists because of its gravitational effects on galaxies and other cosmic structures, but we've never directly observed it. Some theories suggest that dark matter particles might interact through tunneling, offering a potential explanation for their elusive nature. If true, this would not only solve a major puzzle in astrophysics, but also deepen our understanding of quantum tunneling and its role in the universe. On a more speculative note, quantum tunneling might even provide clues about the origin of the universe itself. Some cosmologists propose that tunneling could have played a role in the Big Bang, allowing the universe to transition from a quantum state to the classical, expanding cosmos we see today. This idea, though still highly theoretical, underscores the central importance of tunneling in explaining the universe's most profound mysteries. The study of quantum tunneling isn't just an abstract pursuit for theoretical physicists. It has real-world implications that could transform our understanding of energy and technology. For example, scientists are exploring ways to mimic the conditions of stellar fusion here on Earth. Fusion power, if achieved, could provide a virtually limitless and clean source of energy, revolutionizing how we power our world. Quantum tunneling is a key factor in these efforts, as it's essential for initiating the fusion reactions that release energy. By studying how tunneling operates in stars, researchers hope to unlock the secrets of controlled fusion, bringing us one step closer to solving humanity's energy challenges. In addition to its potential for energy production, quantum tunneling also has applications in quantum computing, where it's used to solve complex problems far faster than classical computers. The principles of tunneling are also critical in understanding semiconductors, the building blocks of modern electronics. These examples highlight the far-reaching impact of quantum tunneling, from the vastness of space to the devices we use every day. As we continue to study quantum tunneling, we're likely to uncover even more surprising connections between the quantum and classical worlds. This research not only deepens our understanding of the universe but also challenges our assumptions about how reality works. It forces us to confront the fact that the rules we take for granted, rules like objects can't pass through barriers, are not as universal as they seem. Instead, they're just approximations of a deeper, more complex reality, one governed by the strange and wonderful laws of quantum mechanics. And yet, for all its strangeness, quantum tunneling is a reminder of the universe's interconnectedness. The same mechanism that powers the stars also shapes the tiniest particles and the most advanced technologies. It's a testament to the elegance and mystery of nature, a phenomenon that defies explanation even as it illuminates the cosmos. The universe's reliance on quantum tunneling highlights a fascinating truth. The cosmos operates on principles that often defy human intuition. In many ways, quantum tunneling serves as a bridge between the impossible and the inevitable, allowing processes that classical physics would deem improbable to occur with startling regularity. This is especially evident in stars, where tunneling ensures their ability to produce the energy necessary for life and the chemical complexity we see in the universe. The role of quantum tunneling in stellar evolution is particularly profound. Stars, the factories of elements, owe their life cycle to the nuclear reactions made possible by tunneling. As stars age, they begin fusing heavier and heavier elements, moving through cycles of nucleosynthesis that culminate in the creation of iron and massive stars. Without tunneling, this chain reaction would halt before it could even begin. And while tunneling primarily enables fusion in the lighter elements like hydrogen and helium, it also plays a role in the fusion of more massive elements, though under even more extreme conditions. This raises an important question: how universal is quantum tunneling across the different kinds of stars? Small, dim stars like red dwarfs, which burn their fuel slowly over trillions of years, also depend on quantum tunneling to sustain their fusion processes. These stars, the most common in the universe, wouldn't shine without it. Similarly, massive stars, which burn through their fuel in mere millions of years, rely on tunneling to achieve the high energy outputs needed to drive their powerful reactions. It's remarkable to think that despite their vast differences in size and lifespan, quantum tunneling serves as the common thread uniting all stars. The phenomenon even extends to exotic stellar remnants like white dwarfs. While these dense, cooling stellar cores are no longer undergoing fusion, their very formation was influenced by quantum mechanics. During the final stages of a star's life, quantum tunneling determines whether it collapses into a white dwarf, explodes as a supernova, or evolves into something even stranger like a neutron star or black hole. In this way, tunneling shapes not only the life of a star but also its eventual demise and transformation. Let's turn our attention to neutron stars, where the physics of quantum tunneling takes on an entirely different character. Neutron stars are the collapsed remnants of massive stars that have gone supernova. They are incredibly dense, with a teaspoon of neutron star material weighing as much as a mountain. In these extreme environments, particles are crushed together so tightly that their quantum behaviors dominate. Some scientists hypothesize that quantum tunneling might still occur in the crust of a neutron star, where nuclei are packed together in strange lattice-like structures. If tunneling is active here, it could help explain the mysterious glitches observed in the rotational speeds of neutron stars, a phenomenon that has baffled astrophysicists for decades. Then there's the intriguing possibility of tunneling near black holes, the ultimate cosmic enigmas. Near a black hole's event horizon, the boundary beyond which nothing can escape, quantum effects are predicted to dominate. Some physicists speculate that tunneling could allow particles to escape the event horizon, a process loosely related to Hawking radiation. While not directly the same as the tunneling in stars, this idea demonstrates how the principles of quantum mechanics continue to play a role in the most extreme conditions imaginable. Quantum tunneling also offers insights into stellar phenomena that we can't yet fully explain. For instance, how do stars form in the first place? The process begins in massive clouds of gas and dust, where gravity pulls material together until it becomes dense enough to ignite fusion. But the transition from a collapsing gas cloud to a shining star involves a delicate interplay of forces, including quantum effects like tunneling. These quantum processes might help explain why some clouds form stars while others remain dormant, shaping the structure of galaxies. In fact, tunneling could be influencing the cosmos on even larger scales. Some researchers propose that quantum tunneling might have played a role in the very early universe, shortly after the Big Bang. During this time, the universe underwent rapid inflation, expanding exponentially in size in a fraction of a second. Tunneling might have allowed this expansion to stabilize, transitioning the universe from a chaotic quantum state to the structured cosmos we see today. This idea, though speculative, underscores the centrality of tunneling in the story of the universe. Even as we explore these cosmic mysteries, quantum tunneling continues to challenge our understanding of physics itself. For example, tunneling is deeply tied to the concept of wave-particle duality, the idea that particles can behave like waves and vice versa. This duality is what allows particles to spread out and appear on the other side of a barrier. But why do particles exhibit this dual nature? What does it tell us about the true nature of reality? These are questions that quantum mechanics has yet to fully answer, leaving open a tantalizing frontier of discovery. The study of quantum tunneling also raises philosophical questions. If particles can tunnel through barriers, does that mean the universe operates on probabilities rather than certainties? And if so, what does that say about the nature of causality and free will? These questions may seem abstract, but they get to the heart of how we understand the universe and our place within it. Looking ahead, the study of quantum tunneling promises to reveal even more surprises. Advances in technology are allowing scientists to simulate stellar conditions more accurately than ever before. These experiments could shed light on the finer details of tunneling, helping us refine our models of stellar fusion. Additionally, new telescopes like the James Webb Space Telescope are providing unprecedented views of stars and galaxies, offering fresh data to test our theories. There's also growing interest in the potential applications of quantum tunneling beyond astrophysics. For instance, researchers are exploring how tunneling could be harnessed to improve energy efficiency in electronics or create new kinds of quantum devices. These technologies could revolutionize industries ranging from computing to renewable energy, showing how the same principles that power stars might one day power our world. But perhaps the most exciting aspect of quantum tunneling is its ability to inspire awe and wonder. The idea that particles can cheat the laws of physics, overcoming barriers that should be insurmountable, challenges our assumptions about what is possible. It reminds us that the universe is far stranger and more beautiful than we can imagine, filled with phenomena that push the boundaries of our understanding. As we continue to study quantum tunneling, we are not just unlocking the secrets of stars. We are uncovering the deeper truths about the nature of existence itself. It's a journey that promises to reshape our understanding of the cosmos and our place within it, revealing a universe that is as mysterious as it is magnificent. The mysteries of quantum tunneling and its role in stellar phenomena stretch far beyond what we've discussed so far. To grasp the profound implications of tunneling, one must also consider its intersection with other fundamental forces and principles of nature, such as gravity, electromagnetism, and the strong nuclear force. Together, these interactions orchestrate the delicate ballet of stellar processes, making tunneling not just a curious quirk of quantum mechanics but a cornerstone of the universe's grand design. One fascinating area of exploration lies in the way quantum tunneling interacts with the strong nuclear force, the force that binds protons and neutrons together in atomic nuclei. The strong force is immensely powerful but operates over extremely short ranges. Within the cores of stars, where densities and temperatures reach unimaginable extremes, quantum tunneling works hand in hand with the strong force to overcome the natural repulsion between positively charged protons. Without tunneling, the sheer electrostatic repulsion between protons would make fusion practically impossible, as classical physics predicts that these particles would never get close enough for the strong force to bind them. Yet, in stars, quantum tunneling enables protons to leap past their mutual repulsion and fuse, releasing tremendous amounts of energy in the process. This energy, in the form of light and heat, is what allows stars to shine. Remarkably, the efficiency of this process varies depending on the size and composition of the star. Massive stars, for instance, achieve higher core temperatures, which increase the likelihood of tunneling events. This allows them to sustain more rapid fusion cycles, producing heavier elements and driving the spectacular phenomena we associate with massive stars, such as supernovae and neutron star formation. On the other end of the spectrum are stars like red dwarfs, whose cooler cores rely on tunneling for much slower fusion processes. These diminutive stars burn their fuel at an astoundingly slow rate, giving them lifespans that can stretch into the trillions of years, far longer than the current age of the universe. The fact that tunneling operates across such a wide range of stellar environments highlights its universality as a physical phenomenon. This universality extends beyond stars themselves, influencing the behavior of other celestial systems. For example, in the early stages of a star's life, when it is still a protostar gathering mass from its surrounding molecular cloud, quantum tunneling may already be at play. Protostars are not yet hot enough for sustained nuclear fusion, but localized tunneling events might occur within their dense cores. These early fusion events could act as a precursor to the main fusion cycle, providing just enough energy to stabilize the protostar and kickstart its evolution into a full-fledged star. The interplay between quantum tunneling and stellar dynamics becomes even more intricate when we consider the life cycles of binary star systems. In these systems, two stars orbit each other closely, often exchanging material. The flow of matter from one star to another can create conditions of extreme density and temperature, which amplify the role of quantum tunneling. In some cases, this can lead to explosive phenomena such as novae, where runaway fusion reactions occur on the surface of one star, temporarily increasing its brightness by orders of magnitude. Binary systems also offer a unique laboratory for studying how quantum tunneling behaves under extreme gravitational forces. For instance, in systems where one star is a white dwarf or neutron star, the intense gravitational pull can compress the infalling material to densities where tunneling becomes a dominant factor. These interactions might even shed light on the formation of exotic objects like magnetars, neutron stars with extraordinarily strong magnetic fields, or the merging of compact objects to form black holes. The connection between tunneling and black holes is another frontier ripe for exploration. While black holes are typically thought of as objects where classical gravity reigns supreme, quantum effects become crucial near their event horizons. The possibility of quantum tunneling in these regions raises profound questions about the fate of matter and energy near black holes. Could tunneling allow particles to escape the seemingly inescapable pull of a black hole? If so, this would have significant implications for our understanding of Hawking radiation, the theoretical process by which black holes slowly lose mass over time. Hawking radiation itself is rooted in quantum mechanics and relies on the concept of particle-antiparticle pairs forming near the event horizon. If one particle falls into the black hole while the other escapes, the escaping particle is observed as radiation. While this is not tunneling in the traditional sense, it illustrates how quantum phenomena challenge the classical notion of absolute barriers, even in the most extreme environments. The study of tunneling in the context of stars and black holes has also led to exciting advances in theoretical physics, particularly in the field of quantum gravity. By attempting to reconcile the principles of quantum mechanics with Einstein's general relativity, researchers are uncovering new ways to think about space, time, and the fundamental forces of nature. Some theories suggest that tunneling could play a role in the emergence of spacetime itself, linking the microcosmic world of particles to the macrocosmic structure of the universe. One particularly compelling idea is that quantum tunneling might have been crucial during the earliest moments of the universe, just after the Big Bang. During this time, the universe underwent a rapid expansion known as cosmic inflation. Quantum fluctuations in this primordial era could have tunneled through energy barriers, creating the seeds of galaxies and other large-scale structures we observe today. If true, this would mean that tunneling is not just a phenomenon of stars but a fundamental process that shaped the very fabric of the cosmos. The implications of quantum tunneling extend to the search for life beyond Earth. In order for life to exist, certain elements, such as carbon, nitrogen, and oxygen, must be abundant. These elements are produced in stars through nucleosynthesis, a process that relies on tunneling to fuse lighter elements into heavier ones. Without tunneling, the chemical building blocks of life would be exceedingly rare, if they existed at all. This means that the existence of life in the universe is, in a very real sense, tied to the quantum processes occurring in stars. Even the conditions for life on planets, like Earth, owe a debt to tunneling. The Sun's steady output of energy, which has remained stable for billions of years, is a direct result of the delicate balance between gravity and the fusion processes enabled by tunneling. This stability has provided the consistent energy input necessary for life to evolve and thrive on our planet. The potential for quantum tunneling to shape the universe doesn't end with its role in stars. Researchers are now investigating whether tunneling could play a role in other astrophysical phenomena, such as the formation of cosmic rays, high-energy particles that travel through space at nearly the speed of light. Some theories suggest that tunneling events in the dense environments of neutron stars or black holes could generate these energetic particles, which then travel across the universe, occasionally colliding with planets like Earth. The study of tunneling also has implications for our understanding of dark matter and dark energy, the mysterious substances that make up the majority of the universe's mass-energy content. While the exact nature of these phenomena remains unknown, some theories propose that they could be linked to quantum processes like tunneling. For instance, dark matter particles might interact with normal matter through rare tunneling events, offering a potential way to detect them. Similarly, tunneling could play a role in the behavior of dark energy, which drives the accelerated expansion of the universe. The more we learn about quantum tunneling, the more it becomes clear that this phenomenon is not just a curious exception to the rules of physics, it is a fundamental aspect of the universe. From the fusion of hydrogen in the cores of stars to the potential creation of new universes in quantum foam, tunneling is a reminder that the cosmos operates on principles far more complex and mysterious than we can fully comprehend. Quantum tunneling has implications that stretch far into the fabric of reality, intertwining with some of the most enigmatic and transformative processes in the universe. To truly grasp its importance, we must examine not only its role in stars but also how it fundamentally challenges our understanding of causality, determinism, and the limits of physical laws. At its core, tunneling is a phenomenon that defies classical intuition. It allows particles to access states or regions of space that seem forbidden by classical physics. This defiance is rooted in the probabilistic nature of quantum mechanics, where particles are described not as fixed entities but as waves of probability. The wave function, which encapsulates all possible states of a particle, can spread beyond physical barriers, giving rise to the possibility of tunneling. This probabilistic nature introduces profound questions about the nature of reality itself. For instance, when a particle tunnels through a barrier, it effectively chooses a path that classical physics would deem impossible. This raises intriguing questions about whether the universe operates with inherent randomness or if deeper, hidden variables govern such phenomena. While the Copenhagen interpretation of quantum mechanics embraces randomness, alternative interpretations, such as the many-worlds theory, suggest that every quantum event branches into a multitude of parallel realities. If quantum tunneling indeed causes such branching, then every tunneling event in the core of a star could potentially generate a cascade of alternate universes. This thought experiment blurs the line between astrophysics and metaphysics, suggesting that the processes driving stellar fusion might also contribute to the creation of an infinite multiverse. Although this idea remains speculative, it underscores the profound interconnectedness of quantum phenomena with the larger cosmos. Returning to the realm of stars, the mechanisms of tunneling not only enable fusion, but also dictate the specific pathways through which elements are formed. For example, in the Sun, the primary fusion process is the proton-proton chain reaction. This reaction relies on tunneling to allow two protons to overcome their mutual electrostatic repulsion and fuse into a heavier nucleus. The probability of this tunneling event is incredibly low, yet the sheer number of protons in the Sun ensures that fusion occurs continuously, powering the star's luminosity. In larger stars, the CNO, carbon-nitrogen-oxygen, cycle becomes the dominant fusion process. This cycle is more complex, involving a series of reactions where tunneling facilitates the fusion of heavier nuclei. The efficiency of tunneling in these environments depends on the star's core temperature and density, which, in turn, are influenced by the star's mass. This delicate interplay determines not only the star's lifespan, but also the types of elements it will produce before it reaches the end of its life. When stars exhaust their nuclear fuel, their fates diverge dramatically based on their mass. Low-mass stars like the Sun will eventually shed their outer layers, leaving behind a dense core called a white dwarf. In contrast, massive stars undergo catastrophic collapse, triggering supernovae that disperse their enriched material into space. During these final stages, tunneling plays a role in the synthesis of the heaviest elements, such as gold and uranium, through rapid neutron capture processes, our process. These elements, forged in the crucibles of dying stars, become the building blocks of planets and life. The intricate connection between tunneling and the creation of elements highlights its role as a cosmic alchemist, transmuting simple hydrogen into the diverse array of atoms that make up the universe. Without tunneling, the periodic table as we know it would not exist, and the universe would remain a barren expanse of hydrogen and helium. Even beyond the life cycle of stars, tunneling continues to shape the cosmos. Consider neutron stars, the remnants of massive stars that have undergone supernova explosions. These dense objects are composed almost entirely of neutrons, packed so tightly that a sugar cube-sized amount of neutron star material would weigh billions of tons. Within their interiors, extreme pressures and densities create conditions where quantum tunneling might enable exotic particle interactions, such as the formation of strange matter or the conversion of neutrons into quark-gluon plasma. Such processes are not merely theoretical. Observations of neutron stars, particularly those in binary systems, provide indirect evidence of these extreme quantum phenomena. When two neutron stars merge, they release gravitational waves, ripples in spacetime that carry information about the event's dynamics. These mergers also produce short gamma-ray bursts and create heavy elements through rapid neutron capture, processes that are deeply intertwined with quantum mechanics. Quantum tunneling's relevance extends to yet another enigmatic phenomenon, black holes. At first glance, black holes seem to be the antithesis of quantum mechanics, dominated entirely by the force of gravity. However, near the event horizon, the boundary beyond which nothing can escape, quantum effects become significant. Theoretical physicist Stephen Hawking famously proposed that black holes emit radiation due to quantum tunneling. This Hawking radiation occurs when virtual particle pairs form near the event horizon, and one particle tunnels out while the other falls in, leading to the gradual evaporation of the black hole. If Hawking radiation is real, it suggests that tunneling can even operate in the most extreme environments imaginable, challenging our understanding of the interplay between quantum mechanics and general relativity. It also raises questions about the ultimate fate of information in the universe. If black holes evaporate through tunneling, what happens to the information they once contained? This information paradox remains one of the greatest unsolved problems in physics, with profound implications for the nature of reality. Another frontier where tunneling plays a crucial role is the study of dark matter and dark energy. Dark matter, which accounts for roughly 27% of the universe's mass-energy content, interacts weakly with normal matter, making it incredibly difficult to detect. Some theories propose that quantum tunneling might allow dark matter particles to occasionally interact with ordinary particles, offering a potential pathway for their detection. Similarly, dark energy, which drives the accelerated expansion of the universe, could involve tunneling events on a cosmological scale, reshaping our understanding of the universe's ultimate destiny. These cosmic mysteries underscore the profound significance of quantum tunneling not only as a phenomenon that powers stars but also as a key to unlocking the deepest secrets of the universe. From the tiniest particles to the largest structures, tunneling serves as a bridge between the quantum and classical worlds, enabling processes that shape the cosmos on every scale. Even as we strive to understand tunneling's role in the universe, its practical applications on Earth continue to expand. Technologies such as tunnel diodes, quantum computing, and even nuclear fusion reactors draw inspiration from the principles of quantum tunneling. These innovations highlight how fundamental research into quantum mechanics can drive technological progress, shaping the future of humanity. Quantum tunneling is more than a scientific curiosity. It is a window into the profound interconnectedness of the universe. By probing the mysteries of tunneling, we not only uncover the mechanisms that power stars but also gain deeper insights into the nature of reality itself, reminding us that the universe is far more intricate and wondrous than we can ever fully comprehend. This journey into the mysteries of quantum tunneling reveals a truth about the universe. The rules that govern reality on the smallest scales are often the most profound and far-reaching. Quantum tunneling is one of these rules, defying classical logic and reshaping our understanding of how the cosmos functions. To explore its deeper layers, let us delve further into its mechanics, applications, and the unanswered questions it raises. The mechanics of quantum tunneling are rooted in the wave-particle duality of quantum mechanics. In classical physics, particles like electrons, protons, or other nuclei are treated as point-like objects with defined positions and velocities. They cannot pass through a barrier unless they possess enough energy to overcome it. Quantum mechanics, however, introduces a different framework. Instead of being localized, particles are described by wave functions, mathematical functions that give the probability of finding the particle in a particular location. The key to tunneling lies in the behavior of these wave functions when they encounter a barrier. Instead of abruptly stopping, the wave function penetrates the barrier, albeit with a rapidly diminishing amplitude. This penetration means there is a small, but non-zero, probability of the particle appearing on the other side of the barrier, even if it does not have the classical energy required to cross it. This leakage of the wave function is what we observe as tunneling. In the dense and energetic cores of stars, tunneling becomes indispensable. Without it, nuclear fusion would be effectively impossible under the conditions present in stars like the Sun. While the temperatures and pressures in stellar cores are immense, they are still not sufficient to overcome the Coulomb barrier, the electrostatic repulsion between positively charged atomic nuclei. It is tunneling that allows protons to cheat their way through this barrier, enabling fusion to occur and powering the star. The rate of fusion in stars depends critically on the tunneling probability, which itself is influenced by factors such as temperature, pressure, and the specific nuclei involved. The mathematics describing this is encapsulated in the Gamow factor, an expression that combines the energy of the barrier, the kinetic energy of the particles, and the likelihood of tunneling. This factor helps astronomers and physicists model the life cycles of stars, from their formation to their eventual demise. Quantum tunneling also plays a central role in understanding why stars shine steadily for billions of years. The improbability of tunneling at any given moment ensures that fusion occurs at a controlled rate. If fusion reactions were purely classical and occurred whenever two nuclei collided, stars would burn through their fuel in mere millions of years. Instead, the delicate balance provided by tunneling ensures that stars like the Sun remain stable for vast stretches of time, providing the conditions necessary for life to evolve. But the implications of tunneling extend far beyond the stellar core. Consider the implications for energy production here on Earth. Fusion reactors, which aim to replicate the processes occurring in stars, must contend with the challenge of achieving the conditions necessary for tunneling to facilitate fusion. Current experimental reactors like ITER rely on achieving extreme temperatures and pressures to mimic the environment of a star's core. However, some researchers are investigating whether quantum mechanics itself can be harnessed to increase the tunneling rate, potentially lowering the energy thresholds required for sustainable fusion. If such advances are realized, they could revolutionize energy production, providing a nearly limitless and clean energy source for humanity. Fusion energy has the potential to replace fossil fuels, reduce greenhouse gas emissions, and address the global energy crisis, all while drawing inspiration from the quantum processes that light up the universe. The study of tunneling has also led to breakthroughs in other fields of science and technology. In electronics, tunneling is the principle behind the operation of devices like tunnel diodes and scanning tunneling microscopes. Tunnel diodes, for example, exploit the rapid tunneling of electrons to achieve high-speed switching, making them useful in high-frequency applications. Scanning tunneling microscopes, on the other hand, use the tunneling current between a sharp tip and a conductive surface to image surfaces at the atomic scale, providing insights into the structure and behavior of materials. These practical applications demonstrate how quantum phenomena, once considered purely theoretical, have tangible impacts on everyday life. They also underscore the interconnectedness of different branches of science, where discoveries in fundamental physics can lead to innovations in engineering, computing, and beyond. Returning to the cosmic scale, quantum tunneling's influence extends to the most extreme environments in the universe. In neutron stars, where densities reach unimaginable levels, tunneling might enable processes that are otherwise forbidden, such as the formation of exotic particles or the decay of neutrons into other states. These processes could provide clues to the nature of matter under extreme conditions and the behavior of fundamental forces. In black holes, tunneling challenges our understanding of spacetime itself. Hawking radiation, as mentioned earlier, relies on tunneling to allow particles to escape from the event horizon, an idea that bridges quantum mechanics and general relativity. The study of such phenomena has led to deeper questions about the nature of information, entropy, and the ultimate fate of black holes. Yet, despite all we know about tunneling, many mysteries remain. For instance, what exactly determines the probabilistic nature of tunneling? Is it truly random, or does it arise from some deeper, hidden mechanism? Can tunneling occur on scales larger than what we currently observe, perhaps even influencing the behavior of galaxies or the structure of the universe? Some theories suggest that tunneling played a crucial role in the early universe, during a period known as cosmic inflation. According to these models, the universe underwent a rapid expansion driven by a high-energy quantum state. Tunneling may have facilitated the transition from this state to the lower energy conditions that allowed matter and galaxies to form. If true, this would mean that tunneling is not just a microscopic phenomenon but a cosmic one, shaping the very fabric of reality. As we continue to explore these questions, one thing becomes clear: quantum tunneling is a cornerstone of both physics and our understanding of the universe. It reveals the limitations of classical thinking, challenges our notions of causality, and opens the door to new possibilities, both in science and in our broader understanding of existence. The story of tunneling is far from over. It is a story of discovery, innovation, and wonder, a reminder that the universe operates on principles far stranger and more beautiful than we can fully comprehend. And as we delve deeper into these mysteries, we are not just studying the cosmos, we are uncovering the very principles that make existence itself possible. The exploration of quantum tunneling opens pathways to profound questions about the universe, the nature of reality, and even the future of humanity. Its implications span across cosmic phenomena, practical technologies, and philosophical reflections. Let us now probe even deeper into its applications, theoretical implications, and the challenges it poses to our understanding. To grasp tunneling's broader significance, consider its impact on cosmology and the birth of the universe. During the inflationary epoch, a period of rapid exponential expansion shortly after the Big Bang, quantum tunneling might have played a pivotal role. Some theories suggest that the universe was initially trapped in a high-energy state. Through a process known as quantum tunneling out of a false vacuum, regions of space transition to a lower energy state, driving inflation. This concept, though theoretical, hints at the possibility that tunneling was the very mechanism that allowed our universe to exist as it does today. This raises another intriguing question: could quantum tunneling have spawned not just one universe but many? The multiverse hypothesis suggests that our universe might be one of countless others, each with its own laws of physics. Tunneling events could trigger the formation of new universes, each budding off from a parent cosmos in a process akin to quantum branching. While such ideas remain speculative, they demonstrate the far-reaching implications of tunneling beyond the stellar scale. Even within our observable universe, tunneling governs processes that affect its large-scale structure. In star-forming regions, where gas clouds collapse under gravity to form new stars, tunneling facilitates the ignition of fusion in the densest regions. This sets the stage for the birth of stars, galaxies, and planetary systems, highlighting tunneling's role as a cosmic architect. Without it, the universe would remain a cold, dark expanse, devoid of the light and energy needed for life. But tunneling isn't just about creation, it also plays a role in destruction and transformation. In dying stars, for example, tunneling helps determine the fate of the core after the outer layers have been shed. In some cases, tunneling allows the fusion of heavier elements, leading to the formation of neutron stars or triggering supernovae. In these explosive events, elements like gold, platinum, and uranium are forged, eventually seeding the cosmos with the building blocks of planets and life. Thus, quantum tunneling is not just a mechanism of fusion, it is a driver of cosmic alchemy. At an even more fundamental level, tunneling challenges our understanding of causality and time. Because tunneling relies on the probabilistic nature of quantum mechanics, it raises questions about the determinism of physical processes. In classical physics, every effect has a clear cause, and every action follows a predictable trajectory. But tunneling introduces a level of unpredictability, where outcomes can only be described in terms of probabilities. This indeterminacy is not just a mathematical quirk, it reflects the underlying reality of the quantum world, where particles do not follow fixed paths but instead exist as waves of possibility. This probabilistic nature also has implications for our understanding of time. In classical physics, time is a continuous and unbroken flow. In the quantum realm, however, processes like tunneling occur on timescales that are inherently uncertain. For example, the time it takes for a particle to tunnel through a barrier is not well defined. It exists as a range of possibilities rather than a fixed duration. Some interpretations of quantum mechanics suggest that time itself might be emergent, arising from the complex interactions of quantum systems. If true, tunneling could provide clues to the nature of time and its relationship to the fabric of space. The enigmatic nature of tunneling also raises philosophical questions about the boundaries of human knowledge. How can something so fundamental to the universe be so counterintuitive? Does the fact that we can describe tunneling mathematically mean we truly understand it, or are we simply scratching the surface of a deeper reality? These questions reflect the broader challenge of reconciling quantum mechanics with our everyday experience of the world. From a technological perspective, tunneling has already revolutionized fields like electronics and nanotechnology. The scanning tunneling microscope, STM, mentioned earlier, not only allows us to image surfaces at the atomic scale but also enables precise manipulation of individual atoms. This has opened the door to the burgeoning field of quantum engineering, where researchers design and build structures atom by atom. Such advances could lead to breakthroughs in quantum computing, materials science, and even medicine. In quantum computing, for instance, tunneling is a key principle underlying the operation of quantum bits, or qubits. Unlike classical bits, which represent information as either 0 or 1, qubits can exist in superpositions of states, thanks to quantum principles like tunneling. This enables quantum computers to perform calculations that would be impossible for classical machines, solving problems in cryptography, optimization, and simulation. While quantum computing is still in its infancy, its potential to transform industries is enormous, and tunneling lies at the heart of this revolution. Yet, as with any powerful tool, tunneling also presents challenges and risks. One of these is the potential for unintended consequences in high-energy experiments. Some have speculated that experiments involving quantum tunneling at extreme scales, such as those conducted in particle accelerators, could create phenomena like microscopic black holes or even trigger vacuum decay. While these scenarios are highly unlikely, they highlight the need for caution and ethical consideration in pushing the boundaries of science. Moreover, the study of tunneling reveals the limitations of our current theories. While quantum mechanics provides a robust framework for understanding tunneling, it does not fully integrate with general relativity, which describes the behavior of spacetime on cosmic scales. This disconnect is a major challenge in modern physics, driving efforts to develop a theory of quantum gravity that can unify these two pillars of science. If successful, such a theory could provide deeper insights into tunneling and its role in the universe. As we continue to unravel the mysteries of tunneling, we are reminded of the interconnectedness of all things. The same process that powers the stars and shapes the cosmos also drives the technologies we use in our daily lives. It connects the microscopic and the macroscopic, the quantum and the cosmic, the theoretical and the practical. It is a testament to the elegance and complexity of the universe, a reminder that even the smallest phenomena can have the greatest significance. And yet, the story of quantum tunneling is far from complete. New discoveries, experiments, and theories will undoubtedly shed more light on this enigmatic process, revealing its secrets and expanding our understanding of the universe. But for now, one thing is certain: quantum tunneling is not just a curiosity of physics, it is a window into the profound and beautiful mechanisms that govern reality. The story of quantum tunneling invites us to push deeper into the mysteries of the universe, not just through scientific inquiry but also through philosophical exploration. It forces us to confront profound questions about the nature of reality, causation, and our own understanding of existence. How can something so abstract, a particle, borrowing energy to overcome an obstacle it seemingly cannot cross, be so foundational to the workings of the cosmos? Let's delve further into how quantum tunneling connects to the fabric of spacetime itself. One of the most fascinating implications of quantum mechanics is the concept of quantum foam, or spacetime foam, as proposed by physicist John Wheeler. On the smallest scales, spacetime is not smooth but rather a frothing, dynamic structure where quantum fluctuations dominate. In this chaotic realm, particles and even entire regions of space can briefly tunnel into states that defy classical description. Quantum tunneling might operate within this foam, providing a mechanism for phenomena such as virtual particles and even the formation of black holes on microscopic scales. If spacetime itself is subject to the laws of quantum mechanics, tunneling could play a role in shaping the very geometry of the universe. This leads to tantalizing ideas about how tunneling might affect the evolution of spacetime on cosmic scales, perhaps influencing the behavior of black holes, wormholes, or the mysterious fabric of dark energy. Dark energy, the force driving the accelerated expansion of the universe, is another arena where quantum tunneling might hold answers. Some theoretical models suggest that dark energy could arise from vacuum fluctuations, which are governed by quantum mechanics. If so, tunneling might play a role in transitioning between different vacuum states, potentially altering the behavior of dark energy over time. While speculative, these ideas highlight the far-reaching implications of tunneling for our understanding of the cosmos. Moving from the vast to the minute, quantum tunneling also forces us to reconsider the nature of particles themselves. In classical physics, particles are discrete entities with well-defined positions and trajectories. Quantum mechanics, however, reveals that particles are better understood as wave-like entities described by a probability distribution. Tunneling exemplifies this duality. A particle does not jump over a barrier in the classical sense but instead exists as a wave that spreads through space, allowing a portion of its probability to leak through the barrier. This wave-particle duality is not merely a mathematical abstraction, but a fundamental feature of reality. It challenges our intuitions and forces us to think in terms of probabilities rather than certainties. This probabilistic nature of quantum mechanics has profound implications, not only for our understanding of physics, but also for how we think about the universe and our place within it. Quantum tunneling also raises questions about the nature of energy and conservation laws. In classical physics, energy conservation is a strict rule. A system cannot gain or lose energy without an external source. Tunneling, however, appears to temporarily violate this rule by allowing particles to borrow energy to pass through barriers. This borrowing is governed by the Heisenberg uncertainty principle, which states that the more precisely we know a particle's energy, the less precisely we can know the time over which it exists. This allows particles to tunnel in ways that seem to defy classical constraints, though the overall laws of conservation remain intact when viewed over larger scales. The implications of this are profound, suggesting that the universe operates not as a deterministic machine but as a probabilistic system where outcomes are governed by chance and uncertainty. This realization has far-reaching consequences, not only for physics but also for philosophy and even theology. If the universe is fundamentally probabilistic, what does that mean for concepts like free will, causality, and the nature of existence? From a practical perspective, understanding tunneling has already led to groundbreaking technological advancements. For example, quantum dots, tiny, semiconducting particles that rely on tunneling effects, are used in a wide range of applications, from medical imaging to advanced displays. These technologies exploit the precise control of quantum effects, including tunneling, to achieve functionalities that would be impossible with classical physics. Similarly, tunneling plays a crucial role in the development of quantum cryptography, which uses the principles of quantum mechanics to create unbreakable codes. By harnessing tunneling and related phenomena, researchers can ensure the security of communication systems against even the most advanced hacking techniques. These practical applications demonstrate that quantum tunneling is not just a theoretical curiosity but a cornerstone of the technological revolution. As we look to the future, the study of quantum tunneling promises to open even more doors. One of the most exciting frontiers is the search for a unified theory of physics, a framework that integrates quantum mechanics with general relativity. Such a theory would provide a deeper understanding of tunneling and its role in the universe, potentially revealing new phenomena and enabling new technologies. For example, some researchers speculate that tunneling could be harnessed to create warp drives or other advanced propulsion systems. By manipulating the quantum properties of spacetime, it might be possible to enable faster-than-light travel, opening the door to interstellar exploration. While such ideas remain speculative, they demonstrate the transformative potential of understanding tunneling and its implications. Even more speculative are ideas about how tunneling might be used to manipulate the fundamental properties of matter and energy. Could we one day use tunneling to create new forms of energy, stabilize exotic particles, or even alter the structure of space-time itself? These questions remain in the realm of science fiction, but they highlight the boundless possibilities of quantum mechanics. At its core, quantum tunneling is a reminder of the universe's complexity and beauty. It reveals a world that operates on principles far beyond our everyday experience, governed by rules that challenge our intuitions and expand our understanding. It connects the smallest particles to the largest structures in the cosmos, shaping the universe in ways that are both subtle and profound. The study of tunneling is more than a scientific endeavor. It is a journey into the heart of reality itself. It challenges us to think beyond the boundaries of classical physics, to embrace the mysteries of the quantum world, and to imagine new possibilities for the future. As we continue to explore this fascinating phenomenon, we are reminded of the limitless potential of human curiosity and the enduring quest to understand the cosmos. Quantum tunneling's profound role in shaping the cosmos doesn't just end with the physical processes of stars or potential technological applications. It serves as a bridge to understanding the very nature of reality. To explore further, let's delve into how this phenomenon relates to broader aspects of quantum mechanics and cosmology, and how it might help us solve some of the deepest mysteries about our universe. One intriguing question is whether quantum tunneling could have played a role in the origin of the universe itself. The Big Bang Theory posits that the universe began as an unimaginably dense and hot singularity, which then expanded into the cosmos we see today. But what caused this initial singularity to break free and initiate the expansion? Some theoretical physicists speculate that quantum tunneling might hold the answer. According to certain models of cosmology, the universe's birth could have been the result of a quantum tunneling event in a pre-existing quantum field. This idea is connected to the concept of false vacuum decay. In this scenario, the universe began in a false vacuum, a metastable state with higher energy. Quantum tunneling allowed a transition to a true vacuum, a state of lower energy. This transition released an immense amount of energy, potentially triggering the Big Bang. The mechanism of false vacuum decay has implications for the future of the universe as well. If our current universe resides in a metastable vacuum, quantum tunneling could one day cause it to transition to a true vacuum, fundamentally altering the laws of physics and potentially bringing the universe as we know it to an end. While this is purely speculative and would occur on timescales far beyond human comprehension, it underscores the profound influence tunneling might have on cosmic evolution. Beyond the Big Bang, quantum tunneling may also play a role in the phenomena surrounding black holes. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. At the edge of a black hole, known as the event horizon, quantum effects dominate. One such effect, proposed by Stephen Hawking, is Hawking radiation. Hawking radiation arises when quantum fluctuations near the event horizon create pairs of particles and antiparticles. Through a process akin to quantum tunneling, one particle escapes into space while the other falls into the black hole. This results in the black hole slowly losing mass and energy over time, eventually evaporating entirely. Without tunneling, this process would be impossible, as the escaping particles must overcome the immense gravitational barrier of the black hole. This connection between tunneling and black holes raises profound questions about the nature of information and entropy in the universe. The information paradox is one of the greatest unresolved problems in physics. It questions whether information about matter that falls into a black hole is lost forever or somehow preserved. Quantum tunneling, as a mechanism underpinning Hawking radiation, could provide insights into this paradox, potentially bridging the gap between quantum mechanics and general relativity. Turning our focus to a more grounded application, quantum tunneling also plays a key role in the field of quantum computing. Traditional computers rely on binary bits, which represent information as zeros and ones. Quantum computers, however, use quantum bits or qubits, which can exist in multiple states simultaneously due to a property known as superposition. Tunneling enables qubits to explore vast numbers of potential solutions to a problem simultaneously by transitioning between energy states in ways that classical systems cannot. This capability has enormous implications for solving complex problems, from optimizing logistical systems to simulating quantum phenomena. For instance, understanding how molecules interact at the quantum level, a task too complex for classical computers, could lead to breakthroughs in medicine, materials science, and energy production. Tunneling, as a fundamental process enabling quantum computation, thus serves as a cornerstone for the next wave of technological innovation. From the microscopic scale of particles to the macroscopic scale of stars and galaxies, quantum tunneling's reach is truly universal. Its principles challenge us to think beyond the constraints of classical intuition, opening the door to new ways of understanding and manipulating the natural world. Yet, the most fascinating aspect of tunneling might be what it reveals about the nature of existence itself. At its core, quantum tunneling exemplifies the principle of uncertainty in quantum mechanics. This principle, famously encapsulated in Heisenberg's uncertainty principle, states that certain pairs of physical properties, such as position and momentum, cannot be simultaneously known with arbitrary precision. Tunneling operates within this realm of uncertainty, showing us that particles are not confined to deterministic paths but instead exist as probabilities spread across space and time. This probabilistic nature of reality is a stark departure from the deterministic worldview of classical physics, where every cause has a predictable effect. For centuries, humanity has sought certainty in its understanding of the universe. Quantum tunneling, however, teaches us to embrace uncertainty and to view it not as a limitation but as a fundamental aspect of reality. This shift in perspective has profound implications for how we think about science, philosophy, and even our daily lives. In the grand tapestry of the cosmos, quantum tunneling is a thread that weaves together the smallest particles and the largest structures, connecting the quantum world to the celestial. It reminds us that even the most counterintuitive ideas can hold the key to understanding the universe's most profound mysteries. As we continue to explore the frontiers of physics, quantum tunneling will undoubtedly remain at the forefront of discovery. Whether through its role in stellar fusion, its implications for the origins of the universe, or its applications in cutting-edge technology, tunneling stands as a testament to the power of human curiosity and ingenuity. In a universe governed by probabilities, quantum tunneling offers a glimpse into the extraordinary possibilities that lie beyond the barriers of classical thought. It challenges us to dream bigger, to question deeper, and to journey further into the unknown. The story of tunneling is far from over, and its mysteries continue to beckon us toward the next great adventure in our quest to understand the cosmos. Quantum tunneling continues to be a gateway to understanding the deepest mysteries of physics, offering insights into both the macroscopic and microscopic realms of existence. As we expand our understanding, the implications of this phenomenon ripple across fields like cosmology, particle physics, and even the philosophy of science, pushing the boundaries of what we believe to be possible. One of the most fascinating aspects of quantum tunneling is its potential role in the multiverse theory. This idea suggests that our universe might be just one of many in an infinite multiverse, each with its own set of physical laws. Quantum tunneling could serve as a mechanism for the creation of these universes. The theory posits that quantum fluctuations in a high-energy vacuum might allow for the nucleation of new universes. Through tunneling, these nascent universes could escape their initial quantum states, expanding and evolving into fully fledged realities, similar to our own. This concept is tied closely to inflationary cosmology, particularly the theory of eternal inflation. Eternal inflation describes a scenario where quantum fluctuations in a scalar field cause regions of space to expand at different rates. While most of space might remain in a state of rapid expansion, quantum tunneling could allow pockets of the universe to transition to slower expansion rates, forming bubble universes. Each of these bubbles could have unique physical constants, leading to a multiverse of infinite diversity. The implications of quantum tunneling in this context are profound. If true, It suggests that the process of tunneling doesn't just shape stars or govern subatomic interactions, but also plays a central role in the very fabric of existence. It could mean that every choice, every possibility, and every imaginable scenario exists somewhere within this vast multiverse, connected through the same fundamental quantum principles. Beyond cosmology, quantum tunneling also raises intriguing questions about the arrow of time. In classical physics, time appears to move in one direction, from past to future, governed by the second law of thermodynamics, which states that entropy, or disorder, always increases. However, at the quantum level, time doesn't operate so rigidly. The equations of quantum mechanics are time-symmetric, meaning they work the same whether time moves forward or backward. Quantum tunneling exemplifies this ambiguity. A particle can tunnel through a barrier in ways that defy classical expectations, seemingly borrowing energy from the future or past to complete its journey. This challenges our traditional understanding of causality and raises the possibility that time might be more fluid than we realize. Could tunneling, in some way, connect different moments in time, offering a glimpse into a more unified theory of space-time? The philosophical implications of this are staggering. If tunneling allows particles to operate outside the constraints of classical time, it suggests that our linear perception of time might be an illusion. This opens the door to radical ideas, such as the possibility of retrocausality, where future events influence the past, or even time travel. While these ideas remain speculative, they underscore the need to rethink our assumptions about time and causality in light of quantum phenomena. On a more practical level, quantum tunneling has also revolutionized our understanding of chemical reactions. At the molecular level, tunneling allows atoms and electrons to interact in ways that classical physics cannot explain. For instance, enzymes, biological molecules that catalyze chemical reactions, often rely on tunneling to transfer protons or electrons between molecules. This process is essential for life, enabling complex biochemical reactions to occur efficiently and rapidly. The study of quantum tunneling in biochemistry has given rise to a field known as quantum biology. This emerging discipline explores how quantum phenomena, including tunneling, play a role in biological systems. From photosynthesis to the functioning of our own DNA, tunneling is proving to be a cornerstone of life's most fundamental processes. In technology, tunneling has already led to groundbreaking innovations, such as the tunnel diode and scanning tunneling microscope, STM. The STM, for instance, exploits tunneling to visualize individual atoms on a surface, providing unprecedented insights into the structure of matter. These advancements are just the beginning. Future technologies, such as quantum sensors and quantum networks, will likely harness tunneling to achieve feats that were once considered science fiction. One exciting prospect is the use of tunneling in quantum teleportation, a process where quantum information is transferred instantaneously between 2 points. While this doesn't involve the physical transfer of matter, it has profound implications for communication and computing. By leveraging tunneling, scientists hope to create networks that transmit data with perfect security and unparalleled speed. As we continue to push the boundaries of what tunneling can achieve, it becomes clear that this phenomenon is not just a quirk of quantum mechanics, but a fundamental feature of reality. It challenges our understanding of the universe at every level, from the origins of stars to the fabric of spacetime itself. What makes tunneling so compelling is its defiance of classical intuition. It forces us to confront the limitations of our understanding and embrace a universe governed by probabilities and possibilities. In doing so, it inspires us to question, to explore, and to imagine new ways of thinking about the world and our place within it. Quantum tunneling is more than just a scientific phenomenon, it's a symbol of the human spirit. It reminds us that barriers, whether physical, intellectual, or existential, are not insurmountable. Just as particles find a way through seemingly impenetrable obstacles, we too can overcome the challenges that lie before us, guided by curiosity, ingenuity, and an unwavering desire to understand the cosmos. The journey of quantum tunneling is far from over, and as we continue to explore its mysteries, we uncover not only the secrets of the universe but also the boundless potential of our own imagination. The story of quantum tunneling is intricately tied to our quest for a grand unified theory, a framework that merges quantum mechanics with general relativity, two of the most successful yet seemingly incompatible theories of physics. Quantum tunneling, with its ability to defy classical boundaries, offers a bridge between these realms, providing clues to the deeper unification of natural laws. Consider the quantum foam, a concept proposed by physicist John Wheeler. At the smallest scales of spacetime, quantum fluctuations dominate, creating a frothy, ever-changing landscape where particles and antiparticles spontaneously pop in and out of existence. Within this foam, tunneling might allow for connections between regions of spacetime, potentially forming wormholes, shortcuts through space and time. Though purely speculative at present, such phenomena could provide the foundation for reconciling gravity with quantum mechanics. One promising avenue for this unification is string theory. String theory posits that the fundamental building blocks of the universe are not particles but tiny, vibrating strings. These strings exist in multiple dimensions, most of which are compactified and invisible to us. Quantum tunneling plays a role in string theory by allowing strings to transition between energy states, or even between different configurations of spacetime. Such transitions might explain phenomena like the creation of black holes or the evaporation of their mass through Hawking radiation. Speaking of black holes, tunneling offers an explanation for one of their most enigmatic properties, Hawking radiation. Proposed by Stephen Hawking, this radiation arises from quantum effects near the event horizon, the boundary beyond which nothing can escape a black hole's gravitational pull. According to quantum theory, particle-antiparticle pairs are constantly forming near the horizon. Occasionally, one particle from the pair tunnels out of the black hole, escaping as radiation, while the other falls in. This process slowly depletes the black hole's mass, leading to its eventual evaporation over astronomical timescales. This interplay of quantum tunneling and black holes raises profound questions about the nature of information. If a black hole evaporates completely, what happens to the information it contained? Classical physics dictates that information cannot be destroyed, yet the fate of information in black holes remains one of the greatest puzzles in physics. Some theories suggest that tunneling might allow information to escape in subtle ways, preserving the fundamental tenets of quantum mechanics. The implications of tunneling also extend to the early universe. During the inflationary epoch, quantum tunneling may have played a crucial role in determining the structure and distribution of matter in the cosmos. Tiny quantum fluctuations, amplified by inflation, seeded the formation of galaxies, stars, and planets. Without tunneling, these fluctuations might never have escaped their initial states, leaving the universe a homogeneous, featureless expanse. As our understanding of tunneling grows, so too does our ability to test its predictions. Advances in experimental physics, such as the construction of more powerful particle accelerators, enable us to probe the conditions under which tunneling occurs. For example, scientists at CERN's Large Hadron Collider, LHC, have explored high-energy collisions that mimic the extreme environments where tunneling becomes significant. These experiments not only confirm the predictions of quantum mechanics, but also hint at new physics beyond the standard model. One of the most exciting prospects for future research is the study of quantum tunneling in extreme astrophysical environments. Neutron stars, for instance, are laboratories of incredible density and gravity, where quantum effects dominate. In these stars, tunneling likely governs the behavior of particles in ways we are only beginning to understand. By observing neutron stars and other exotic objects, astronomers can glean insights into the interplay between quantum mechanics and relativity. Moreover, tunneling might hold the key to unlocking the secrets of dark matter and dark energy, two of the most mysterious components of the universe. Dark matter, which makes up about 27% of the universe's mass-energy content, interacts with ordinary matter through gravity but remains invisible to electromagnetic radiation. Tunneling could provide a mechanism for interactions between dark matter particles, offering clues to their identity. Similarly, dark energy, the force driving the universe's accelerated expansion, might involve tunneling phenomena at a cosmic scale. On a philosophical level, quantum tunneling challenges our understanding of determinism and free will. In a classical world, events are deterministic. Given enough information, we can predict the future with perfect accuracy. But in the quantum realm, probabilities rule. Tunneling epitomizes this uncertainty, showing that outcomes can occur without a deterministic cause. This raises profound questions about the nature of reality, choice, and the role of consciousness in shaping the universe. For centuries, humanity has grappled with the idea of causality, the principle that every effect has a cause. Tunneling disrupts this notion, allowing particles to cheat the rules of classical physics. This invites us to reconsider the boundaries between the possible and the impossible, encouraging us to dream bigger and explore further. In the realm of science fiction, the idea of harnessing tunneling for practical applications has captured imaginations worldwide. Could we one day develop technologies that exploit tunneling to traverse vast cosmic distances, effectively enabling faster-than-light travel? While current physics prohibits such travel, tunneling offers a tantalizing hint that the universe might harbor shortcuts we have yet to discover. At its core, quantum tunneling is a testament to the beauty and complexity of the universe. It reveals a cosmos where the improbable becomes possible, where barriers are mere illusions, and where the mysteries of existence beckon us to explore. As we continue to unravel the secrets of tunneling, we are reminded that the universe is not a static, mechanical entity but a dynamic, ever-evolving tapestry of wonder. The journey of understanding tunneling is far from over. With every experiment, every observation, and every breakthrough, we inch closer to a more complete picture of reality. And in this quest, we are guided by the same principles that define tunneling itself: persistence, curiosity, and the ability to overcome barriers, no matter how insurmountable they may seem. Quantum tunneling, as a phenomenon, continues to inspire awe not just because of its counterintuitive nature, but because of its universality. It is not confined to stars, black holes, or particle physics laboratories. It happens everywhere, constantly, even within us. For instance, tunneling is essential in processes like radioactive decay, where particles escape atomic nuclei, and even in modern technology, where devices like transistors and tunneled diodes rely on this very principle to function. Let's take a moment to explore how quantum tunneling manifests in the technology that shapes our daily lives. At the heart of many of our electronic devices are semiconductors. These materials rely on carefully engineered energy barriers to control the flow of electrons. Quantum tunneling enables electrons to pass through these barriers, allowing devices like microchips and processors to perform computations at astonishing speeds. Without tunneling, modern computing as we know it would not exist. The smartphone in your pocket, the internet you're using, and even advanced medical imaging technologies like MRI scanners are all, in some way, reliant on quantum tunneling. But tunneling's role in our lives goes beyond the tangible. It's a window into the underlying nature of the universe. Consider this: if tunneling occurs constantly at the atomic and subatomic levels, then every structure around us, from buildings to our own bodies, exists in a delicate balance maintained by quantum effects. The solidity of matter itself, as governed by the Pauli exclusion principle and the behavior of electrons, owes much to the principles of quantum mechanics. Now, zooming out to a cosmic scale, quantum tunneling continues to redefine how we think about the universe's birth and evolution. In the context of the Big Bang, tunneling may have played a pivotal role in the initial symmetry-breaking events that led to the diversity of particles and forces we observe today. According to some cosmological models, the early universe existed in a highly energetic, unstable state. Through tunneling, it transitioned to a lower-energy, stable configuration, a process akin to rolling down a hill, but with a quantum twist. This transition not only shaped the structure of the cosmos but also determined the properties of fundamental particles. As we study quantum tunneling in stars and elsewhere, one of the most intriguing questions arises: could tunneling also allow for the creation of entirely new universes? In theoretical physics, the idea of false vacuum decay suggests that our universe might not be in its most stable state. Quantum tunneling could, in principle, cause a sudden transition to a more stable vacuum state, creating a new universe in the process. While this is an abstract and highly speculative idea, it underscores the profound implications of tunneling in shaping not just stars, but the very fabric of reality. Another fascinating aspect of tunneling lies in its relationship with time. In classical physics, time flows in one direction, forward. But in the quantum world, the concept of time becomes less rigid. When particles tunnel, they effectively bypass classical trajectories, completing actions in ways that seem to defy temporal constraints. This has led some physicists to speculate about connections between tunneling and the nature of time itself. Could tunneling provide insights into time travel or the possibility of reversing time? While these ideas remain in the realm of speculation, they highlight the profound philosophical questions tunneling raises. From a practical standpoint, understanding tunneling better could lead to groundbreaking advancements in energy production. For example, nuclear fusion, the process that powers stars, remains one of humanity's most sought-after energy sources. If we could replicate the conditions under which tunneling facilitates fusion, we could unlock a virtually limitless supply of clean energy. Current fusion experiments, like those conducted at ITER, the International Thermonuclear Experimental Reactor, are already benefiting from our understanding of tunneling, even if we're still far from achieving sustained fusion. The potential applications of tunneling don't end there. In the realm of quantum computing, tunneling is a cornerstone of how qubits, quantum bits, operate. Unlike classical bits, which can be either 0 or 1, qubits can exist in superpositions of states. Quantum tunneling enables qubits to explore multiple possibilities simultaneously, vastly increasing the computational power of quantum computers. Yet, for all its practical implications, quantum tunneling remains a mystery at its core. Why does the universe operate this way? What deeper principles underlie quantum mechanics? Some physicists suggest that tunneling may hint at a multiverse, a collection of parallel universes where every possible outcome of a quantum event actually occurs. In this view, tunneling isn't just a quirk of our universe, it's a glimpse into the broader, interconnected reality beyond our comprehension. As we contemplate these ideas, it's worth reflecting on the broader philosophical implications of quantum tunneling. At its essence, tunneling reveals that barriers are not absolute, that the universe operates on principles of possibility rather than certainty. This challenges not only our understanding of physics but also our worldview. It invites us to question the nature of limitations, to consider that what seems impossible may simply require a different perspective or approach. Quantum tunneling is, in many ways, a metaphor for human curiosity and perseverance. Just as particles can tunnel through barriers that seem insurmountable, so too can we, as a species, overcome the limits of our knowledge. Every discovery about tunneling, every breakthrough in understanding the universe, is a testament to our ability to push beyond the boundaries of what we think is possible. Quantum tunneling is far more than an esoteric concept confined to theoretical physics. It is a fundamental force that shapes the stars, powers our technologies, and challenges our understanding of reality itself. By studying tunneling, we not only unlock the secrets of the universe but also reaffirm our place within it, as explorers, thinkers, and dreamers. The story of tunneling is the story of the cosmos and our ongoing quest to understand it. Quantum tunneling continues to be a reminder of how the universe operates on principles that often defy our intuitive understanding. Its influence spans from the smallest particles to the grandest cosmic structures, weaving a narrative of interconnectedness and mystery. To truly appreciate the implications of quantum tunneling, we must delve deeper into its theoretical underpinnings, experimental confirmations, and its broader philosophical ramifications. One of the most captivating aspects of quantum tunneling lies in its role within quantum field theory, the framework that combines quantum mechanics with special relativity. In this theory, particles are no longer seen as tiny billiard balls but rather as excitations of underlying fields that permeate the universe. These fields are dynamic, constantly fluctuating, and filled with potential energy barriers. Tunneling is a direct result of these fluctuations, as particles momentarily borrow energy to traverse classically forbidden regions. This concept of borrowing energy ties into Heisenberg's uncertainty principle, a cornerstone of quantum mechanics. The principle states that certain pairs of properties, like position and momentum, cannot both be precisely known at the same time. This uncertainty allows particles to temporarily exist in states that would otherwise violate classical conservation laws. During tunneling, this uncertainty provides a brief loophole that enables particles to overcome barriers they couldn't surmount in a classical sense. Consider the Coulomb barrier, which plays a critical role in nuclear fusion. In stars, nuclei must overcome this electrostatic repulsion to fuse. However, without tunneling, the energy required to do so would be orders of magnitude higher than what stars can naturally provide. Tunneling bridges this gap, allowing fusion to occur even at the relatively low temperatures and pressures found in stellar cores. This interplay between quantum mechanics and thermodynamics highlights the delicate balance that sustains the energy output of stars for billions of years. But quantum tunneling isn't just about breaking barriers, it also highlights the probabilistic nature of the universe. Unlike classical physics, where outcomes are deterministic, quantum mechanics deals in probabilities. Tunneling exemplifies this, as particles do not decide to tunnel in a deterministic sense. Instead, there is a calculable likelihood of tunneling occurring, determined by factors like the height and width of the potential barrier. This probabilistic nature raises profound questions about causality and free will. If the fundamental building blocks of reality operate on probabilities, to what extent can we say that events are caused? And if causality is not absolute at the quantum level, how does this influence our understanding of macroscopic systems, including human consciousness? Some researchers have speculated that quantum mechanics, and by extension tunneling, might play a role in the processes of the brain, potentially influencing decisions and creativity. While this idea remains speculative, it underscores the philosophical depth of quantum mechanics. On an experimental level, tunneling has been confirmed through numerous observations and applications. One of the earliest confirmations came from the study of alpha decay, a type of radioactive decay where an alpha particle tunnels out of an atomic nucleus. This phenomenon was first explained using quantum tunneling, providing a groundbreaking example of how quantum mechanics governs phenomena that classical physics cannot. In modern laboratories, tunneling is observed and harnessed through technologies like the Scanning Tunneling Microscope, STM. This device uses tunneling to map the surface of materials at the atomic level, allowing scientists to visualize individual atoms and molecules. The STM operates by bringing a sharp metal tip extremely close to the surface being studied. As electrons tunnel between the tip and the surface, they create a measurable current that varies with the distance between the two. This current provides a detailed map of the material's atomic structure, revolutionizing fields like nanotechnology and materials science. Another fascinating experimental confirmation of tunneling comes from Josephson junctions, which consist of two superconductors separated by a thin insulating barrier. In these systems, tunneling allows pairs of electrons, known as Cooper pairs, to pass through the barrier without resistance. This phenomenon forms the basis of superconducting quantum interference devices, SQUIDs, which are used in highly sensitive magnetometers and quantum computing. Beyond its practical applications, quantum tunneling has also become a tool for exploring the limits of our understanding of physics. For instance, experiments involving ultracold atoms and optical lattices have allowed physicists to create highly controlled environments where tunneling can be observed in real time. These studies not only deepen our understanding of tunneling but also test the predictions of quantum mechanics itself. As we push the boundaries of experimentation, new questions emerge about the fundamental nature of tunneling. One of the most intriguing areas of inquiry involves the tunneling time problem. How long does it take for a particle to tunnel through a barrier? This seemingly simple question has sparked decades of debate among physicists, as tunneling challenges conventional notions of time. Some theories suggest that tunneling occurs instantaneously, while others propose that it involves measurable, albeit extremely brief, durations. Resolving this question could provide new insights into the relationship between quantum mechanics and time. Philosophically, tunneling challenges us to rethink the nature of barriers and boundaries, not just in physics, but in life itself. At its core, tunneling is about overcoming obstacles that seem insurmountable. It demonstrates that the impossible may be possible, given the right conditions and perspective. This idea resonates deeply with the human spirit, inspiring us to explore, innovate, and transcend our limitations. Moreover, tunneling invites us to ponder the interconnectedness of all things. In a universe where particles can influence each other across vast distances, where barriers can be crossed without direct contact, and where probabilities govern outcomes, the boundaries between self and other, here and there, begin to blur. This interconnectedness is a reminder that we are not isolated entities but part of a larger, dynamic whole. As we continue to study quantum tunneling, we are not just uncovering the mechanics of the universe, we are also uncovering the nature of reality itself. Tunneling is a gateway to understanding the profound mysteries that define existence, from the birth of stars to the emergence of consciousness. It is a testament to the power of curiosity and the limitless potential of human inquiry. Quantum tunneling is more than just a physical phenomenon, it is a profound insight into the workings of the cosmos, touching every aspect of existence from the microscopic to the cosmic scale. To fully appreciate its implications, we must delve into its mathematical foundation, explore its implications for the origin of the universe, and consider its role in technological advancements that continue to shape our understanding of the quantum realm. At the heart of quantum tunneling lies the Schrödinger equation, the cornerstone of quantum mechanics. This equation describes the behavior of quantum systems and predicts the probability of a particle's position and energy. When applied to tunneling, the Schrödinger equation reveals that the wave function of a particle, its mathematical representation, does not abruptly drop to zero at a potential barrier. Instead, it decays exponentially but remains non-zero, indicating a finite probability that the particle will appear on the other side of the barrier. This subtle yet profound insight distinguishes quantum mechanics from classical physics. The mathematics of quantum tunneling also introduces the concept of the tunneling amplitude, which determines the likelihood of a particle successfully tunneling through a barrier. This amplitude depends on factors such as the height and width of the barrier, the particle's energy, and its mass. Heavier particles or higher barriers result in lower tunneling probabilities, which explains why tunneling is primarily significant at the atomic and subatomic scales. However, the fact that it occurs at all challenges our classical notions of determinism and causality. One of the most extraordinary applications of quantum tunneling lies in the context of the early universe. During the Big Bang, quantum tunneling likely played a critical role in the process known as cosmic inflation, a brief but intense period of exponential expansion. Inflationary models suggest that quantum fluctuations in the early universe allowed regions of space to tunnel between different energy states, driving the rapid expansion that smoothed out irregularities and set the stage for galaxy formation. Without quantum tunneling, the universe as we know it might never have taken shape. Tunneling also provides a framework for understanding Hawking radiation, a theoretical prediction about black holes. According to Stephen Hawking, black holes are not entirely black but emit radiation due to quantum effects near their event horizons. This process involves particles and antiparticles appearing spontaneously near the event horizon. Occasionally, one particle escapes while the other falls into the black hole, creating the appearance of radiation. Quantum tunneling is integral to this phenomenon, as it enables particles to escape the immense gravitational pull of the black hole, defying classical expectations. Beyond theoretical physics, tunneling has practical applications in fields ranging from electronics to medicine. The development of tunnel diodes, which exploit tunneling to achieve extremely fast switching speeds, revolutionized early electronics and laid the groundwork for modern semiconductor technology. Similarly, the quantum tunneling of electrons through biological molecules is essential for processes such as photosynthesis, where it enables the efficient transfer of energy in plants. In the realm of medicine, tunneling is leveraged in technologies like magnetic resonance imaging, MRI, which relies on quantum properties to create detailed images of the human body. Tunneling phenomena are also central to advancements in quantum computing, where qubits, quantum bits, can exist in multiple states simultaneously, thanks to quantum superposition and tunneling. These advancements promise to revolutionize computing by solving problems that are currently intractable for classical computers. The exploration of quantum tunneling also pushes the boundaries of our experimental capabilities. Researchers are continually developing new techniques to study tunneling phenomena under extreme conditions, such as ultra-cold temperatures and high magnetic fields. These experiments not only confirm theoretical predictions but also reveal unexpected behaviors that challenge our understanding of quantum mechanics. For instance, recent studies have observed tunneling in systems where classical physics would predict complete suppression, suggesting that our current models may be incomplete. Philosophically, quantum tunneling invites us to reconsider our relationship with time and space. The notion that particles can traverse barriers without passing through the intervening space challenges our linear perception of movement and causality. It suggests that reality is not confined to the dimensions we experience, but is instead a complex interplay of probabilities and potentials. Moreover, tunneling highlights the limitations of human perception. Our classical intuition, shaped by everyday experiences, often fails to grasp the counterintuitive nature of the quantum world. This disconnect serves as a humbling reminder of the vastness of the unknown and the importance of maintaining an open mind in the face of new discoveries. Tunneling, in this sense, is not just a physical phenomenon but a metaphor for the pursuit of knowledge, a journey into the unknown where barriers are overcome through perseverance and curiosity. The implications of quantum tunneling extend far beyond the confines of physics. They influence our understanding of biology, chemistry, cosmology, and even philosophy. By enabling processes that are essential to life, such as enzymatic reactions and energy transfer, tunneling underscores the interconnectedness of all things. It demonstrates that the principles governing the stars also govern the molecules within our cells, uniting the microcosm and macrocosm in a single, elegant framework. As we continue to explore the mysteries of quantum tunneling, we are reminded that the universe is far more complex and beautiful than we can imagine. Each discovery opens new doors, revealing deeper layers of complexity and interconnection. Whether we are studying the fusion of stars, the birth of galaxies, or the quantum processes within our own bodies, tunneling provides a bridge between the known and the unknown, inviting us to explore the infinite possibilities of existence. The exploration of quantum tunneling is also paving the way for breakthroughs in the field of nanotechnology. At the nanoscale, where quantum effects dominate, tunneling is not just an anomaly, it's a fundamental mechanism that defines how matter behaves. Researchers are using this principle to develop nanodevices with unprecedented precision and efficiency. For example, scanning tunneling microscopes, STMs, which rely on tunneling, allow us to visualize and manipulate individual atoms and molecules. In the realm of energy, quantum tunneling has potential implications for nuclear fusion technology, the same process that powers the stars. On Earth, replicating the conditions necessary for fusion requires overcoming immense technical challenges, such as achieving the extreme temperatures and pressures found in stellar cores. However, understanding how tunneling facilitates fusion in stars could lead to innovative approaches for initiating and sustaining fusion reactions at lower energies. If successful, fusion could provide a nearly limitless and clean energy source, transforming our energy landscape and addressing global challenges like climate change. Tunneling also plays a critical role in understanding radioactive decay, a process central to fields ranging from geology to medicine. In radioactive decay, atomic nuclei emit particles, such as alpha particles, through quantum tunneling. Although the particles lack the energy to overcome the nuclear binding force according to classical physics, tunneling allows them to escape. This phenomenon not only explains the stability and instability of certain elements but also enables techniques like radiocarbon dating, which scientists use to determine the age of ancient artifacts and geological formations. In the biological realm, tunneling is integral to enzyme function, the catalysts of life. Enzymes facilitate chemical reactions by lowering the energy barriers that separate reactants and products. Quantum tunneling allows particles, such as protons and electrons, to traverse these barriers with remarkable efficiency, enabling processes like cellular respiration and DNA repair. Without tunneling, life as we know it would not be possible, as the chemical reactions essential for survival would occur too slowly to sustain biological systems. Furthermore, tunneling challenges our understanding of determinism and randomness in the universe. In classical physics, The behavior of objects is predictable, governed by deterministic laws. However, quantum mechanics introduces an element of unpredictability. The probability of a particle tunneling through a barrier is not fixed but depends on the statistical nature of the wave function. This inherent randomness has profound implications for the nature of reality, suggesting that the universe operates not on certainty, but on probabilities. This realization has sparked philosophical debates about free will and causality. If the fundamental building blocks of the universe are governed by probabilities, what does this mean for the deterministic view of cause and effect? Some argue that quantum mechanics provides a scientific basis for free will, as it introduces an element of unpredictability into the fabric of existence. Others contend that even randomness is not synonymous with freedom, as it lacks intent or agency. Regardless of the perspective, quantum tunneling compels us to re-examine our assumptions about the nature of existence. Quantum tunneling also inspires artistic and metaphorical interpretations, symbolizing the transcendence of barriers and the possibility of achieving the seemingly impossible. In this context, tunneling represents a journey of discovery, a leap into the unknown that leads to profound insights and breakthroughs. It reminds us that even the most impenetrable obstacles can be overcome with perseverance and a willingness to embrace uncertainty. The study of tunneling has also advanced our understanding of time. In quantum mechanics, time is not an absolute entity but a parameter that influences the behavior of particles. Tunneling introduces the concept of tunneling time, the duration a particle takes to traverse a barrier. This concept has sparked debates among physicists, as different interpretations yield varying results. Some theories suggest that tunneling occurs instantaneously, while others propose finite timescales. Resolving these discrepancies could provide deeper insights into the nature of time and its role in the universe. Tunneling's connection to time is particularly intriguing in the context of cosmology. If time itself emerged from quantum fluctuations during the Big Bang, then tunneling may have played a role in shaping the temporal fabric of the universe. This idea raises profound questions about the origins of time and its relationship to space, matter, and energy. Could tunneling be the key to understanding the arrow of time, the unidirectional flow from past to future? If so, it may hold the answers to one of the greatest mysteries in physics. From a technological perspective, the implications of tunneling extend to quantum communication and cryptography. Quantum tunneling enables the transmission of information through secure channels, as the principles of quantum mechanics prevent eavesdropping without detection. These technologies promise to revolutionize data security, ensuring the privacy of information in an increasingly digital world. By harnessing the power of tunneling, we can create communication systems that are not only faster but also fundamentally more secure than current methods. Moreover, quantum tunneling is a cornerstone of quantum computing, a field poised to revolutionize computation. Unlike classical computers, which process information in binary bits, quantum computers use qubits that can exist in multiple states simultaneously. This capability, made possible by quantum superposition and tunneling, allows quantum computers to solve complex problems at unprecedented speeds. As we continue to unravel the mysteries of quantum tunneling, we are reminded of the interconnectedness of science, philosophy, and technology. Each discovery not only deepens our understanding of the universe but also inspires new questions and challenges our assumptions. Tunneling serves as a bridge between the known and the unknown, inviting us to explore the uncharted territories of the quantum realm. At its core, quantum tunneling is a testament to the resilience of the human spirit, the drive to push boundaries, defy limitations, and uncover the truths that lie beyond the horizon. It challenges us to think beyond the confines of classical logic, to embrace uncertainty, and to recognize the beauty and the complexity of existence. As we journey further into the quantum world, we are not merely observers but active participants in the unfolding story of the universe, a story shaped by the interplay of chance, choice, and discovery. The journey into quantum tunneling is not merely a scientific endeavor but a philosophical exploration into the nature of reality itself. The very existence of tunneling disrupts our classical view of the universe, where every action has a predictable consequence. It shows us that the quantum world operates under rules that defy our everyday logic, rules that are probabilistic rather than deterministic, fleeting rather than concrete. And yet, it is within this uncertainty that the cosmos finds stability, stars ignite, and life thrives. Consider the broader implications of quantum tunneling for cosmology. If particles can traverse barriers via tunneling, it implies that processes that seemed impossible under classical physics are, in fact, achievable. This principle may have been fundamental in shaping the earliest moments of the universe. During the inflationary period of the Big Bang, when spacetime expanded faster than the speed of light, quantum fluctuations likely played a significant role in the formation of structures we see today, such as galaxies and stars. Some theories suggest that tunneling events during this phase may have contributed to the generation of the matter-antimatter asymmetry, a cornerstone of our observable universe. This asymmetry, where matter came to dominate over antimatter, remains one of the greatest mysteries in cosmology. Without this imbalance, matter and antimatter would have annihilated each other completely, leaving the universe devoid of stars, planets, and life. It's possible that quantum tunneling, by allowing certain particles to escape annihilation, tipped the scales just enough to leave a surplus of matter. If true, this would position tunneling as a key player in the very existence of the cosmos. Tunneling's role in the early universe may also extend to the creation of black holes. Under certain conditions, massive stars collapse under their own gravity, forming singularities from which not even light can escape. Some physicists theorize that quantum tunneling could allow for the escape of energy or information from these enigmatic objects, a phenomenon known as Hawking radiation. This radiation, first proposed by Stephen Hawking, arises from quantum effects near the event horizon of a black hole and could ultimately lead to its gradual evaporation over immense timescales. The possibility of tunneling near black holes raises profound questions about the nature of information in the universe. In classical physics, information is preserved. Every action, no matter how chaotic, leaves behind a trace. However, black holes appear to challenge this principle, as anything falling into them seems to vanish without a trace. Quantum mechanics, particularly the phenomenon of tunneling, may hold the key to resolving this paradox. If tunneling allows information to escape from black holes in some form, it would have far-reaching implications for our understanding of the universe's fundamental laws. The connection between tunneling and black holes doesn't end there. Wormholes, theoretical passages through spacetime that could connect distant regions of the universe, may also rely on quantum tunneling. While wormholes remain speculative, they are solutions to Einstein's equations of general relativity under specific conditions. For a wormhole to remain stable, exotic matter with negative energy density would be required. Quantum tunneling might provide the mechanism for such exotic matter to manifest, potentially making these pathways more than just mathematical curiosities. If tunneling can facilitate the existence of wormholes, it could revolutionize our understanding of space travel, opening the door to faster-than-light journeys and even time travel. Beyond cosmology, tunneling offers a glimpse into the quantum fabric of space itself. At the Planck scale, the smallest measurable scale of the universe, spacetime may not be smooth but instead consists of a seething foam of quantum fluctuations. Particles and virtual particles constantly pop in and out of existence, a process made possible by tunneling. This, quantum foam, suggests that spacetime itself is dynamic and mutable, challenging our traditional notions of a fixed, unchanging universe. It's within this foam that the seeds of stars, galaxies, and possibly even entire universes are sown. The concept of a multiverse, an ensemble of universes, each with its own physical laws, gains traction when viewed through the lens of tunneling. If tunneling allows particles to escape seemingly impenetrable barriers, could it also allow entire regions of spacetime to split off and form new universes? This idea aligns with theories like eternal inflation, where the universe is constantly spawning new, bubble universes, through quantum tunneling processes. If true, this would mean our universe is just one of countless others, each shaped by the strange and unpredictable rules of the quantum world. Quantum tunneling also intersects with our understanding of dark matter and dark energy, the mysterious forces that dominate the universe. Dark matter, which accounts for roughly 27% of the universe's mass energy content, interacts with regular matter in ways that defy classical physics. Could tunneling provide the mechanism for these interactions? Similarly, dark energy, responsible for the universe's accelerated expansion, may arise from quantum effects in vacuum energy. By studying tunneling, scientists hope to uncover clues about these elusive phenomena, potentially rewriting the story of cosmic evolution. As we delve deeper into the mysteries of quantum tunneling, it becomes clear that its implications extend far beyond the stars. It challenges the very fabric of what we perceive as real, showing us that the universe operates on a scale where the improbable is not just possible but essential. Every breakthrough in our understanding of tunneling brings us closer to answering questions that have puzzled humanity for centuries. Why does the universe exist? How did it come to be? What is the ultimate nature of reality? Yet, for all its complexity, tunneling also carries a simple, poetic truth: even the most insurmountable barriers can be crossed. In the grand dance of particles and forces, where barriers loom and paths seem blocked, tunneling reminds us that progress often comes from the unexpected, from the leap into the unknown. It's a lesson not just for science but for life itself, a testament to the power of persistence, curiosity, and the human spirit. The narrative of quantum tunneling continues to unravel itself as a phenomenon that not only influences stars and cosmic processes, but also touches upon the most fundamental aspects of matter, energy, and existence itself. At its heart lies a paradox that defies common sense. A particle can exist on both sides of an energy barrier without seemingly having passed through it in a conventional way. This strange reality suggests that the universe itself operates on principles that are probabilistic rather than absolute, chaotic yet coherent. To fully grasp tunneling's significance, we must consider its relationship to the quantum wave function, a mathematical representation that describes the probabilities of a particle's location, momentum, and other properties. The wave function doesn't just describe the particle as it exists, it predicts where it could potentially be. When an energy barrier is encountered, the wave function doesn't stop, it extends into the barrier and beyond. The phenomenon we call quantum tunneling occurs when this wave function allows for the particle to appear on the other side of the barrier, even though classical physics deems it impossible. This is where the interplay between quantum mechanics and thermodynamics becomes fascinating. The process of nuclear fusion in stars requires hydrogen nuclei to overcome their mutual electrostatic repulsion, or Coulomb barrier, caused by their positive charges. Classical physics would insist that the temperatures within most stars are insufficient for this to occur on a large scale. Yet, quantum tunneling ensures that these reactions happen billions of times per second, allowing stars to shine and release the energy that sustains the universe. It's a testament to how quantum mechanics rewrites the rules that govern reality. The specific mechanics of tunneling within a star involve a delicate balance of probabilities. Hydrogen nuclei, or protons, within a star's core move at extremely high speeds due to the immense temperature and pressure. While the majority of these particles lack the energy to overcome the Coulomb barrier directly, a small fraction manage to tunnel through it thanks to quantum mechanics. This process initiates the proton-proton chain reaction, where hydrogen nuclei fuse to form helium, releasing vast amounts of energy in the form of light and heat. But quantum tunneling's role isn't limited to stars like our Sun. In massive stars, it drives more complex fusion reactions, including those that create heavier elements like carbon, oxygen, and iron. These elements, forged in stellar cores, are later dispersed into space through supernovae, seeding the cosmos with the building blocks of planets, moons, and life itself. Without tunneling, the universe would lack the diversity of elements that make its incredible complexity possible. Tunneling's reach extends beyond the stars to the origins of the universe itself. During the Big Bang, when the universe was unimaginably hot and dense, quantum effects dominated the behavior of particles. It's thought that tunneling played a role in symmetry breaking, the process through which the forces of nature, such as electromagnetism and the strong nuclear force, differentiated from a single, unified force. This breaking of symmetry led to the formation of matter as we know it, providing a foundation for the universe's evolution. This interplay between quantum tunneling and cosmic evolution brings us to one of the most profound questions in physics. Could tunneling have facilitated the very existence of the universe? According to some interpretations of quantum mechanics, the universe could have emerged from a quantum fluctuation within a vacuum, a momentary blip, in an otherwise featureless expanse of nothingness. If this is true, tunneling might have allowed this fluctuation to expand and evolve into the vast, intricate cosmos we see today. This hypothesis places tunneling at the very origin of everything, from the stars to the galaxies to life itself. Tunneling also provides a critical lens through which we can explore the behavior of particles under extreme conditions. For example, within neutron stars, objects so dense that a sugar cube-sized portion would weigh billions of tons, quantum effects dominate. Neutron stars are essentially giant atomic nuclei, and the interactions between particles in these environments are governed by quantum mechanics, including tunneling. The incredible density and pressure create conditions where particles must tunnel to rearrange themselves, influencing the star's structure and evolution. The study of tunneling in such environments may even offer insights into the enigmatic realm of quantum gravity, the yet undiscovered theory that unites general relativity and quantum mechanics. Tunneling suggests that the fabric of spacetime itself may not be static but rather subject to fluctuations and distortions at the quantum level. These distortions could manifest as wormholes, pathways that connect distant points in spacetime. While purely theoretical at this stage, wormholes capture the imagination as a tantalizing possibility for interstellar travel, or even glimpsing other universes. Beyond astrophysics and cosmology, quantum tunneling has practical applications here on Earth, bridging the gap between the cosmic and the everyday. The phenomenon underpins technologies such as scanning tunneling microscopes, which allows scientists to image surfaces at the atomic scale. It's also fundamental to the operation of semiconductors and quantum computers, which rely on tunneling to manipulate information at the smallest possible scales. These technologies not only revolutionize our ability to explore the universe but also transform our understanding of quantum mechanics itself. As we explore tunneling's implications, one thing becomes clear: it's a phenomenon that connects the smallest scales of reality with the largest. It serves as a reminder that the universe is deeply interconnected, governed by laws that are simultaneously simple and profound. From the quantum foam of spacetime to the fiery cores of stars, tunneling shows us that the improbable is often the engine of the cosmos. And yet, for all its complexity, tunneling remains a deeply human story, a testament to our species' ability to probe the unknown and make sense of the seemingly incomprehensible. By studying this phenomenon, we've not only uncovered the secrets of stars but also gained a deeper appreciation for our place in the universe. Tunneling is a reminder that even in the face of insurmountable odds, progress is possible, barriers can be overcome, and the impossible can become reality. As we continue exploring quantum tunneling, it's important to emphasize just how revolutionary this concept has been in the development of modern physics. At first glance, it seems almost counterintuitive that particles can bypass barriers they should, according to classical physics, never be able to pass. This strange behavior of particles, exhibiting both wave-like and particle-like properties, has been pivotal in the shift from Newtonian mechanics to quantum mechanics, fundamentally altering our understanding of how nature works at its core. The idea that particles can tunnel through barriers once thought impassable was first proposed in the 1920s by physicist George Gamow, building on the work of others in quantum theory, including Niels Bohr and Albert Einstein. Gamow's insight provided an explanation for the phenomenon of alpha decay in radioactive elements, where particles inside an unstable nucleus tunnel through the potential barrier to escape, even though they don't have enough energy to overcome the barrier according to classical physics. Gamow's theory was extended to nuclear fusion in stars, where it was found that quantum tunneling plays a crucial role in overcoming the Coulomb barrier that prevents the fusion of hydrogen nuclei. At the incredibly high temperatures and pressures inside stars, hydrogen nuclei move at speeds fast enough to approach one another closely enough for tunneling to occur. This allows nuclear reactions to take place in stars despite the apparent barrier of electrostatic repulsion between positively charged protons. What makes tunneling so powerful in the context of stellar fusion is its probabilistic nature. Unlike classical physics, which often provides a deterministic outcome, quantum mechanics operates on probabilities. The likelihood of a particle tunneling through a barrier depends on several factors, including the energy of the particle, the thickness of the barrier, and the characteristics of the wave function associated with the particle. In stars, this means that even though most particles might not have enough energy to overcome the barrier in the classical sense, a small but significant fraction can still tunnel through. This is the key to the continuous nuclear fusion reactions that power stars. The significance of quantum tunneling in stars cannot be overstated. It is the very mechanism that allows stars to shine, generating the light and heat we rely on. Without it, stars would not be able to undergo the nuclear fusion that fuels their energy output. The fact that tunneling allows fusion to occur even at temperatures much lower than those predicted by classical models is a testament to the intricacies of the quantum world. In fact, without quantum tunneling, stars like our Sun wouldn't exist in their current form, and life as we know it might never have had the necessary energy source to emerge. Beyond stellar fusion, quantum tunneling is implicated in some of the most fascinating and unexplained phenomena in the cosmos. For instance, it's thought that tunneling could be a key ingredient in understanding the origins of the universe itself. During the Big Bang, quantum fluctuations could have caused a temporary distortion in the fabric of space-time, potentially allowing the creation of matter from a vacuum. This process, called quantum creation, may have involved tunneling through energy barriers that separated a vacuum state from a state of high-energy matter. In this sense, quantum tunneling may have played a direct role in the formation of the universe. Furthermore, tunneling might even hold the answers to some of the most mysterious cosmic objects, such as black holes. Theoretical physicists have speculated that tunneling could be the mechanism behind the formation of the event horizon of a black hole, or even the cause of black hole evaporation, a process known as Hawking radiation. According to the theory proposed by physicist Stephen Hawking in 1974, black holes could emit radiation due to quantum effects near the event horizon, where particles and antiparticles are created and annihilate each other. Under certain conditions, one of these particles could tunnel through the event horizon, escaping into space while the other falls into the black hole. This process might slowly cause the black hole to lose mass over time, ultimately leading to its evaporation. On an even more speculative note, quantum tunneling could provide a potential solution to some of the greatest challenges in theoretical physics, such as the search for a unified theory of everything. If quantum mechanics and general relativity can be successfully reconciled through a theory of quantum gravity, tunneling could be the key that unlocks a new understanding of the very fabric of space-time. Tunneling may play a role in explaining phenomena like wormholes, hypothetical shortcuts through spacetime that connect distant parts of the universe. If wormholes are possible, they could offer a way to travel across the cosmos faster than the speed of light, potentially revolutionizing our understanding of space travel. The implications of quantum tunneling stretch beyond just the confines of theoretical physics and astrophysics. They also have practical applications here on Earth. Quantum tunneling is at the heart of the functioning of semiconductors, which are used in virtually all modern electronic devices, from smartphones to computers to televisions. In these devices, the flow of electrons through barriers is essential to their operation, and tunneling plays a crucial role in enabling this process. Without quantum tunneling, the development of transistors, key components of modern electronics, would have been impossible. Moreover, tunneling is an essential principle behind the operation of scanning tunneling microscopes, STMs, which allows scientists to observe surfaces at the atomic scale. These microscopes work by measuring the tunneling current between a sharp tip and the surface being studied, enabling them to create detailed images of individual atoms. The ability to visualize and manipulate atoms has opened new doors in materials science, nanotechnology, and medicine, where understanding the properties of matter at such a small scale can lead to groundbreaking discoveries. Looking toward the future, tunneling could also play a critical role in the development of quantum computers. These computers, which harness the strange properties of quantum mechanics, use quantum bits or qubits to process information in ways that classical computers cannot. Quantum tunneling could be used to facilitate quantum operations, such as enabling qubits to transition between different states in ways that classical bits cannot. This could lead to computers capable of solving problems that are currently beyond the reach of even the most powerful supercomputers. As research into quantum computing progresses, it's likely that tunneling will play an increasingly important role in the advancement of this technology. Tunneling's connection to quantum mechanics also highlights one of the most puzzling aspects of the universe: the inherent uncertainty that governs the behavior of particles. In classical physics, we are accustomed to deterministic laws where the future can be predicted given enough information. But in the quantum world, uncertainty reigns supreme. The Heisenberg uncertainty principle states that certain pairs of physical properties, such as a particle's position and momentum, cannot both be precisely measured at the same time. This intrinsic uncertainty gives rise to probabilistic events like tunneling, where particles can appear in places where they have no classical right to be. This randomness may seem disconcerting at first, but it also opens up new possibilities for our understanding of the universe. In the quantum world, certainty is replaced by probability, and the laws of physics no longer follow the predictable rules of classical mechanics. The behavior of particles is influenced by wave functions, which describe the likelihood of finding a particle in a given state or location. Quantum tunneling, therefore, becomes just another manifestation of this strange and wondrous probabilistic world. The continued study of tunneling may hold the key to some of the most profound questions in physics, including the nature of dark matter and dark energy. These mysterious substances make up a vast majority of the universe's mass and energy, yet they remain elusive to our most advanced instruments. Could tunneling play a role in revealing the properties of these enigmatic forces? It's a question that may take decades or even centuries to answer, but one thing is certain: the discovery of quantum tunneling has already reshaped our view of the cosmos in ways that we are still beginning to understand. Ultimately, quantum tunneling serves as a reminder of how much there is yet to learn about the universe. From the formation of stars to the nature of the cosmos itself, tunneling is a phenomenon that touches every corner of the universe. It challenges our perceptions, defies our expectations, and reminds us that reality is far stranger than we ever imagined. And as our understanding of quantum mechanics continues to evolve, there is no telling what other mysteries tunneling may help us unravel. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.